great pleasure to be here, and thank you all for coming. And it's a great pleasure to talk to you about materials at Queen Mary, and congratulations on being first-year students at Queen Mary. So, advanced materials really can help to solve major world problems, and I'm going to talk about that. And I'm going to talk about two materials in this talk. One is gallium nitride, GaN, which is already changing the world, and I'll talk about that. And Harry's talk was great, and with these functional materials, they tend to be simpler materials. So turbine blades contain, you know, many different elements, maybe 15 different elements. Gallium nitride, just 2 elements, gallium and nitrogen. And I'm also going to talk about a material which just contains 1 element, which is carbon, and graphene has the potential to change the world. And both are called functional materials or device materials, and Harry talked about structural materials. I'd like to say just at this time, you have the potential to change the world, you really do. So someone in this audience may well be changing the world in the future, or several people. So what are the most important recent materials? And one way of answering that question is to say which materials have won Nobel Prizes most recently. And in 2010, 2 scientists working at Manchester University, 2 Russian scientists, Gallium and Novoselov, got the Nobel Prize for graphene, and the citation was for groundbreaking experiments regarding a 2-dimensional material, graphene. And we'll see why it's called a 2-dimensional material later. And then in 2014, 3 Japanese scientists got the Nobel Prize, and this was a citation for the invention of efficient blue LEDs based on gallium nitride, which will enable bright and energy-saving white light sources. So arguably, these are 2 really important new materials, and I've built upon the work of these Nobel Prize winners. So I've been fortunate to be involved in both these materials, first at Cambridge. So a lot of the work I'll talk about was done at Cambridge, but then at Queen Mary, and I moved to Queen Mary in 2018, and we're developing the work, particularly on graphene, at Queen Mary. So, and one thing which, as Harry has mentioned in his talk, one thing that material scientists do, we really go from basic science through to exploitation. So, you know, if you're a physicist or a chemist, you do really interesting, important basic science. But if you're a material scientist or an engineer, you're also interested in useful science. You really want to make the science of science useful to people, useful to society, curing diseases, having people's computers go faster and so on, and being more efficient. So in material science, we go from basic science to exploitation, and we have huge benefits to society from materials. And I'll talk about saving energy, saving carbon emissions. So if you're really interested in going to net zero, then material science is essential to do this. And we create jobs with materials, we save lives, and we improve our health. And I'll touch on some of these things in my talk. So let's start with LEDs. LEDs particularly made from gallium nitride. And this is a quotation, a few quotations from a report that Goldman Sachs issued. You've probably heard of Goldman Sachs, a big world-leading investment banking company. And this was a report they wrote in 2016. And they said, the rapid adoption of LEDs in lighting marks one of the fastest technology shifts in human history. So if you go back, if you go back to when you were born, then the lighting in the world then was probably incandescent lighting, incandescent light bulbs. And now it's in developed countries, it's LEDs, and in many developing countries, LEDs as well. So that's a really rapid change. And then they made, and few changes that are that rapid. They then made this other statement in a later section of their report: the LED industry is the top industry disruptor amongst green energy industries. Okay, and if you look at wind power or solar power, then they're saying LEDs are actually the top industry compared with wind power and solar power and other energy industries. And then these are predictions from the USA Department of Energy made in 2015 for the year 2030. And they said if LED costs come down and the efficiency goes up, and that's happening, so costs are coming down, the efficiency is going up, then the LEDs will have 86% of the lighting market in the USA. And that's probably happened already. So, it's happened very rapidly before the 2030 prediction. And then they said, and this is again looking at 2030, the electricity savings from LEDs will be twice the savings generated by wind power and 20 times the savings generated by solar energy. So really quite surprising predictions in a way. And the annual savings in energy will be $40 billion due to LEDs in the year 2030, and with no subsidies. And then in the report, they say the energy used for lighting in 2035 will be 75% lower than it would have been if LEDs had not entered the market. So not just 10% lower, but 75% lower, which is a huge reduction in energy use. And then if you look at the combined energy savings in the world from 2015 to 2035, so energy savings in America, $630 billion in avoided energy costs. So these are really huge figures. They dwarf the cost of COVID, for example, right? So this is the savings, financial savings from using LED light. So this is why gallium nitride LEDs are so important. If you go back to when you were born, then lighting then can use 20%, 1/5 of all electricity used in the UK. And globally, the figure was much the same. In countries like Thailand, which didn't have much industry, lighting was 40% of all electricity. And as the USA DOE report said, LEDs will reduce this figure, this 20% figure, by 75%. So lighting with LEDs then uses 5% of electricity instead of 20%. So if you use LED lighting, replace lighting by LEDs, you save 15% of all electricity. And if that electricity is generated in fossil fuel power stations, you save 50% of carbon emissions. And these are really huge carbon savings. In the USA, the savings, 40 billion per annum electricity costs. In the USA, the savings from going totally to LED lighting are 5 billion a year. And it's a very large saving. And as Harry said, these large numbers are hard to take in often. So let me give you an illustration. The government asked someone called Dilnot to prepare a report, and the object of this report was to say how much extra money do we have to use to really look after all the old people in the UK properly, right? So in addition to what we're spending now, how much extra you have to use? And Dilnot said £2 billion a year, and the Treasury looked at this and said, we can't afford it, and put it on one side. So with LED lighting, because the UK is on mainly to LED lighting already, we're on the way to saving £5 billion per year. So you could easily actually afford to fund all the extra care for old people from the savings already being generated by using LED lighting in the UK. So how is this light emission achieved? If you go back in time, then you needed all these semiconductors on the right-hand side of this diagram to achieve light emission going from the infrared up to the blue at the top. And in fact, zinc selenide, ZNSE, for emitting in the blue never worked very well. So if you go back 20 years, go back to your birth, we had no semiconductor which emitted efficiently blue light. It just didn't exist. And that's why we didn't have blue LEDs or white LEDs 20 years ago. If you look at the left-hand side of the diagram, you'll see gallium nitride, which emits in the near ultraviolet, and indium nitride below, which emits in the infrared. And you can mix these two compounds and have indium gallium nitride, a compound with 3 atoms. And it's a bit like cookery. If you have about 10% indium, you get blue light out. If you have 25% indium, you get green light out. So just by varying this composition, you can get light emitted of any color. And these materials on the left-hand side, they do not exist in nature. So the elements, of course, exist. So the gallium and the nitrogen is there, but you will not find gallium nitride in nature. So these are materials which are being made by material scientists. They're new materials, and we can design them. So we're really being creative, and this was designed with the object of getting out light of this color. So again, modeling, which Harry's referred to, you can calculate gallium nitride will emit near light in a near ultraviolet. You must calculate that. So if you make it, that's what you expect to get out. So as Harry said in the past, material science was largely trial and error work. Now it's really basic science where we can design new materials which don't exist in nature. And this is just a schematic of what an LED looks like. So the active element of an LED is these what are called quantum wells, these stripes of indium gallium nitride. This is an electron micrograph at high magnification. The horizontal lines, you see in here, right, each of these horizontal lines, that's an atomic plane of atoms which is being imaged. Right, so very high resolution. And this indium gallium nitride is called a quantum well. It's so thick, it's so thin, called a quantum well. And that's about typically here, you can see from the scale bar, that quantum well is about maybe 4 nanometers across. And typically in LEDs, they're 2, 3, or 4 nanometers across. And then that active system is part of the LED structure. And basically you have what's called P-type GaN on the top and N-type GaN on the bottom. You pass an electric current through, and to be a bit more technical, you actually inject electrons into the bottom of each quantum well. You inject what are called holes, which you won't get to come across properly until you do your semiconductor course. You inject holes into the top of the quantum well, and then the electrons and holes combine in the quantum well, and they give out light of this energy. So depending on the composition of the InGaN, they'll give out light, blue light, or green light, or red light. So that's how the LEDs work. And if you want white light, okay, I remove the white light slide because it's getting too long at all. If you want white light, you take a blue LED and you cover it with a phosphor, and the blue light excites yellow light in the phosphor, and that combination of blue and yellow gives you white light. And if you look at someone's white LED that's on the front of their bike, so often bikes will have LED front lights now. When the bike's coming towards you, the light often looks a bluish white, and then as it goes past you, if you look, it may be a yellowish white, and that's because the phosphor isn't very uniformly coated onto the blue LED. So I got involved in this work in about 1995, and in 2002, LEDs were really expensive. So I well remember in 2002, there was an article in the newspaper which said that Prince Philip was buying LEDs for Buckingham Palace because they're so good, and they cost £50 each. And that's far too expensive for the general public to use. So I thought, why are they so expensive? And they're expensive for 2 reasons. One is the gallium nitride was deposited on either sapphire or silicon carbide wafers. The sapphire was artificially grown sapphire, and 2-inch diameter wafers. And sapphire and silicon carbide are really expensive, and 2-inch wafers are quite expensive as well. And so I had the idea to reduce the costs so that everyone could use LED lights and grow on silicon wafers, and silicon is much cheaper than sapphire or silicon carbide, and also to grow on 6-inch diameter silicon wafers, which are also quite cheap. And you can get about 10 times as many LEDs on a 6-inch diameter wafer as on a 2-inch diameter wafer. And the reason for that is that you're comparing areas. It's the area of the device you can get it on. And so a 6-inch wafer has 3 times the diameter of a 2-inch wafer. And so a 6-inch wafer has 9 times the area, right? It's the diameter squared of the 2-inch wafer. And so you get 9 times as many devices on a 6-inch wafer. And then there's what are called edge effects around the edge of the wafer where the LEDs don't work so well. And so actually the edge effects are less on one 6-inch wafer than on 9 2-inch wafers. And so you get about 10 times as many wafers. And it's as cheap to process a 6-inch wafer as a 2-inch wafer. So the size of the wafers brings down the cost as well. And I had a research student. I gave him this project in 2002. That was to try and grow gallium nitride devices on silicon, and we got a quick grant and everything. But I'd just like to say to you, you can start thinking now. I know you're in your first year, but some of you might be interested in being research students, so just think about that now, get it in your mind. If you would like to do research, then there's lots of projects at Queen Mary. And if you want to be a research scientist, it's a really good opportunity for you to get involved in this. So he had this research project, and there were 3 challenges. It's much more difficult to grow gallium nitride on silicon than it is on sapphire. That's why people hadn't done it. These were the 3 materials challenges. The first is that there's a large lattice mismatch between the gallium nitride lattice and the silicon lattice. So one way of looking at this is, if you look at the separation of atoms in silicon, it's very different from the separation of atoms in gallium nitride. And this difference is about 17%. And so when you deposit gallium nitride on silicon, the gallium nitride tries to use the silicon atoms in the surface, that arrangement atom, as a template. And it tries to put down the gallium nitride atoms on this silicon template. You have this large lattice mismatch, and it's accommodated by defects called dislocations. And you can fuzzy picture dislocations up the top. So that's one thing, you have to solve that problem, because the dislocations quench the light emission. So the electrons and holes, instead of recombining the quantum well, they combine at the dislocations and don't give out light. So the other problem to solve is that you're growing at 1,000 degrees centigrade, a very high temperature, and the thermal expansion coefficient of silicon and gallium nitride is very different, more than 54%. And when you grow at growth temperature and then cool down, the gallium nitride contracts more. Let's get it right. Because the silicon contracts, the gallium nitride contracts less than the silicon, and so the silicon puts the gallium nitride into tension, and it cracks. And so you get cracking, very visible cracking. So this is an optical image of a wafer that's really badly cracked. So that's a problem to solve. And then the third problem to solve is, when you put a gallium nitride on silicon, you actually get a reaction, a chemical reaction between the two. You get gallium silicon eutectic formed, that gallium silicon compound formed, and you don't want that as well. So these are 3 major problems. And when I propose this to the research student, I say it's a big challenge. And people would say to me, "You're crazy, Colin, you're crazy to try this, because these problems, you'll never succeed." And this very good research student actually did succeed. And I'll just tell you a little how you solve these problems. So you can't deposit gallium nitride directly on silicon. And so what you do, you put an intermediate layer in, sometimes called a buffer layer, and we use aluminium nitride as the intermediate layer. And aluminium nitride doesn't react with silicon, so, well, it doesn't react in the same way with silicon. And so you can use that and then put the gallium nitride on top of the aluminium nitride. But the quality of this aluminium nitride layer on silicon is really important. And one way you can look at this interface between the two is to do electron microscopy, which Harry has already referred to. This is high resolution electron microscopy, where this is aluminium nitride on the top, this is silicon on the bottom, and these dots are atoms, right? These are real atoms. You're looking at this at over 100 million times magnification, right? This is hugely magnified, and you can, if people say to you, "We don't believe in atoms," you can say, "You can see them. They really exist." These are like dumbbells, like 2 close together, because the silicon structure has 2 atoms very close together. And you can control each of these 2 atoms. So that's what you see. And when we took this picture, we totally unexpectedly, we didn't expect to see this, that in the middle, instead of having a sharp interface between the aluminium nitride and the silicon, you see there's this amorphous layer, which we thought was probably silicon nitride. And in the electron microscope, you can do chemical analysis on an atomic scale, because when you bombard the material with electrons, X-rays are emitted, and those X-rays are fingerprints of the element. So if you look at silicon, for example, and an electron beam, then what is called silicon K-alpha X-rays are emitted, for example, a specific X-ray energy, and so you can do analysis. So at school, you're used to using test tubes for analysis. you can analyze every atom. You can actually focus the beam down to an atomic diameter and move the beam one after the other, and you can say what each atom is. It's incredibly powerful. And Queen Mary is having installed at the moment a brand new electron microscope which will have atomic resolution. So, you know, and these instruments are not cheap. I mean, Harry talked about the cost. This electron microscope cost is about £1 million. I think we're paying £1 million. It's actually the list price is significantly more than that. So very, very expensive equipment, because to resolve single atoms, you need to have an electron beam so you can focus down to an atomic size. So, you know, and in your final year project, you might possibly get to use this new microscope which is here. So, again, it's taller than me, and it's highly automated, and it's just a wonderful instrument. So, another problem to solve. So, okay, so that problem was solved by using this buffer layer. Another problem to solve is this huge difference in the thermal expansion coefficient between the two materials when you cool down from the growth temperature of 1,000 degrees centigrade, which puts the gallium nitride in tension. And so what we did then was we deliberately introduced into the gallium nitride, as we were growing it, another material, which was aluminium gallium nitride, and that actually puts the material under compressive stress. So we balance the tensile stress on the gallium nitride from the silicon with the compressive stress of this aluminium gallium nitride layer. So this is really straight engineering at the atomic level. And in fact, to achieve unstressed, uncracked gallium nitride, we put in 4 of these layers, and each one was graded. So we actually grew aluminium gallium nitride as a graded composition of gradually increasing aluminium content. And we got uncracked, totally uncracked layers. So this was that. So this was how that problem was solved. And then the third problem was this high dislocation density, and we used a silicon nitride mask, and this again was deposited in the growth reactor, and it was less than 1 monolayer thick. So what do I mean by less than 1 monolayer thick? Well, it's a monolayer thick layer with holes in it. And if you deposit for the right length of time, so you don't get a complete layer, you get a layer with holes in it, and the dislocations are stopped where the mask is, but where the holes are, the dislocation propagates through, but also the growth propagates through. But the mask itself, you can reduce the dislocation density by 100 times towards the magnitude. So we solved all these problems, and this student managed to get LED structures, not very efficient to start with, but he demonstrated it could be done. And then after further work, in 2009, this was a 6-inch wafer of gallium nitride on silicon, and these patterns are LEDs. It's a test structure, so it's LEDs of different sizes, and that's the blow-up on the top right, and this is just an individual LED, and this is just passing these two electrodes that are just two contacts, passing electric current through. And this is emitting blue light, which is so bright it's saturated the detector, so it looks like white light. And this was the first gallium nitride LED system on 6-inch silicon in the world, which we did in 2009. And it was, we used industrial fabrication silicon to process it. That's where this company comes in. And then I talked about exploiting the research. So what we did was to set up a couple of companies, and just to try and get this into the marketplace. And then another company called Plessy acquired these companies, and people said to go from your lab experiment to industrial production will take at least 2 years. And the company hired 3 of my postdocs, which was very sensible, and this transition from lab to industry happened in 8 weeks, so it was very, very rapid. And they started manufacturing. So they acquired the company in 2012, started manufacturing in 2013, and by 2014, they were making and selling 2 million LEDs. So this was just very rapid exploitation. And just to bring, hopefully this will Okay. First, so it's the first manufactured LEDs in the UK and the first commercially available LEDs anywhere in the world of gallium nitride on silicon. And to bring this now totally up to date, hopefully, yes. So what's happened now to this company, it's moved into micro LEDs. So really small gallium nitride on silicon LEDs, about a micron across. It's still based on our technology and my research group. And Facebook in 2020, they were looking for people, a partner for making micro LEDs. And out of the various companies in the world who are trying to make micro LEDs, they chose Plessy as the best. And so there's now a partnership, and Facebook, you all know better than me, they changed their name recently, or part of it. Anyway, Facebook want to use these micro LEDs for augmented reality headsets, so that in bright sunlight, you can go out into the street, and these LEDs are so bright, you can see the images in your headset or in glasses. So it won't be a big headset. You'll have glasses with just on the end of the glasses, these little LEDs, micro LEDs, and so on. And there's a potential to use micro LEDs for next generation TVs. So at the moment, the original TVs were liquid crystal display screens, and then we went to OLEDs now, which are very good. But even better will be micro LEDs, even better picture, and they'll consume much less energy. So again, it'll be saving energy. Right, and so this now gives you some figures for energy saving from gallium nitride. For lighting, we've said gallium nitride LEDs are saving 15% of all electricity usage. I haven't had the time to talk about electronic devices. So gallium nitride electronic devices can replace silicon power electronic devices and save another 10% of electricity. And the electronic devices are about 10 years behind the LEDs, but they're improving rapidly, and they're already replacing silicon power electronics. So let me give you an example. Some of you will say, I want a new laptop, and you go to a shop and you think, I want one light so I can carry it around, and you buy this ultralight laptop, and it's delivered to you by the shop attendant, and you think, this feels a bit heavy. And the reason is that the charger is this sort of big, quite heavy box. And that's because it contains silicon power electronics. Now, the chargers you'll get now, that silicon has been replaced with gallium nitride power electronics, and it's shrunk in size, and it consumes a lot less energy, and it's a lot lighter to use. So these electronic devices made from gallium nitride already happening. So what's remarkable is that people who use gallium nitride LEDs and also power electronics can save 25% of global electricity from this one material. And this is not a lot of hype in a pipe dream, because it's happening with LEDs and it's starting to happen with the power electronic devices. So it's just extraordinary that we can get this sort of saving and also get 25% CO2 savings if the electricity comes from fossil fuel power stations, which in most of the world it does. So achieving net zero, and when I said we've helped to solve the world's problems, sorry, let me look at my watch. So help to solve the world's problems, then gallium nitride really is starting to do this. I'll give one health example now for gallium nitride. So this is purifying water. So if you go off the visible spectrum, you can get deep UV light emitted, if you remember that diagram. I added some aluminium to have aluminium gallium nitride. And radiation of about 270 nanometer wavelength, it damages nucleic acid, which is contained in both DNA and RNA, so it's contained both in bacteria and viruses. And when you irradiate by 270 nanometers, you destroy the ability of the DNA and RNA to reproduce, and so you kill the bacteria, and you effectively kill the viruses because they can't reproduce. And you also kill other things like fungi and so on, and mosquito larvae, right? So it's really good for purifying water. And we can achieve that emission at that wavelength, and we can show if you expose water for long enough at this wavelength, it just kills all the bugs in it. The problem is that whereas the efficiency of, in the visible wavelength, the efficiency of white and blue LEDs is very high, the efficiency of deep UV is only about 1%. And that's because the problem largely of reducing the defects where the methods we use for the visible structures don't work so well for deep UV. So in 2018, the efficiency was only about 1%. And it's a material science problem. So if you want to save literally millions of lives, you work on this problem and make these devices more efficient so that you can purify water all around the world. And what's happened since 2018 is the efficiency has improved, not as much as we'd like, it has improved. It's improved enough that all deep UV emitters, LEDs, are now being used in, for example, air conditioning systems, where they're being used inside. So as the air recirculates, you expose this air to the UV radiation, and that kills all the bugs in the air. So that is being used, and it's being used at a time of COVID. So it really is now saving lives. So these health implications are really important. Right, move on to graphene. So graphene got the Nobel Prize, and it's a two-dimensional network of carbon atoms. It's sometimes called carbon chicken wire for, I'll show you a picture in a moment. What's important about carbon is it is a single layer of carbon graphene, single layer of carbon atoms. All the carbon atoms are in a single plane, and it is the thinnest material in the world. And it was isolated in 2004 by these two Manchester Nobel scientists. And what they did, they took a block of graphite. Now, graphite is multi-layer graphene, and graphite is a mineral. You dig it up from the earth. And in Cumbria, in the UK, for example, there's graphite mines there. People just dig into it all over the world. It's not uncommon, right? All over the world, there's graphite. And so these two Nobel Prize winners, they had this idea, and they said, why don't we put some Scotch tape or sellotape on both sides of a lump of graphite and just pull the tape apart, and we get two thinner blocks of graphite. Then we put another piece of sticky tape on and pull apart. And you keep doing this repeatedly, pulling a block of graphite apart, and it gets thinner and thinner and thinner until you're down to one atomic layer. And they did that, and they got the Nobel Prize. So most simple science experiments have been done, but not all. So here's a simple science experiment. You could have thought of this, right? I could have thought of it. And these simple experiments still exist. And they got the Nobel Prize. And they're tiny flakes of graphene you get when you do this. They're a few millimeters across. And they're useful now. They're being used to add to car tires and paint and concrete and tennis rackets, running shoes. It is said they improve their performance. What isn't clear, and Harry has looked into this, Harry Badisha, you may get the same improvements by adding, say, carbon black. But this is the use at the moment. If you want to make electronic devices, you cannot manufacture like this. Actually, getting down to a single layer takes about 45 minutes, and you've got tiny, tiny flakes, and you just can't manufacture. So that's been the problem. We need larger area graphene to get electronic and optical devices. And so this is, on the left-hand side, any of you who know people who keep chickens, they're kept in. You have a big area of land, and they're kept in by wire, which looks like this. It's got this hexagonal structure, and this is why it's called chicken wire. And so it's a sort of graphene structure. And it's graphite is just many layers of this graphene. And so when you pull it apart, you get fewer and fewer layers of graphene until you get a single layer. And now this is an amazing picture. It is again a high resolution electron micrograph, and you can really see. So this is, I should say, when we looked at the previous picture where I said we're looking at single atoms, that was true, but it was a three-dimensional object, and you're looking at single atom columns, right? You're looking end-on at single atom columns, and you're resolving each single atom column. Here, so there might be many atoms in this single atom column. Here, these really are monolayer, and each one here is an atom. So you can see the hexagonal structure of graphene. And what's remarkable about this picture is that this graphene has had an impurity deliberately added, silicon, to dope it, to change its electronic properties. And the silicon atom, because it's bigger than the carbon atom, it can either replace two atoms in the structure, or replace one atom of the structure. And the properties are very different according to where the silicon goes. And so to study it, again, the electron microscope really essential. And you get these remarkable pictures, I think, of single atoms, and then seeing this white blob. It is a single silicon atom, right, which is replacing 2 carbon or 1 carbon. Now, the 2 Mensa scientists didn't really get the Nobel Prize just for Scotch tape, because if the graphene had been no good, people would have said, well, a silly thing to do, a silly experiment. But they got the Nobel Prize because they got the graphene, and then they did experiments on it, and a single layer of graphene is transparent, so you can't see it. So think of doing experiments when you can't see it. Think of putting contacts on when you can't see it. So they did these really difficult experiments, and what they showed was amazing, and that was this layer of graphene had conductivity 1,000 times better than copper. And because it's got high conductivity, then it promises high-speed electronics, right? The electrons move fast, much faster than in silicon. Because it has high conductivity, it has low resistivity, and so that promises low power consumption. Again, lower power consumption than silicon devices. It's very flexible, high thermal conductivity, so that promises increased device performance. Because if we come back to gallium nitride power electronics, they can't operate at their theoretical efficiency because you can't conduct the heat away fast enough. So the gallium nitride power electronics only operates at about 1/3 of what they could operate at if you could get the heat conducted away faster. So with graphene, you've got this high thermal conductivity, so increased performance, highly transparent, a single layer is 97% graphene. I should say, in my bag here, I have another object, a large pencil. People are listening online. You should come into some of these lectures because you don't see some of the demonstrations. It's a very large pencil, right? And the lead in the pencil is actually graphite. And what happens is when you write with a graphite, when you write, right, you actually you're laying down when you write. You're laying down a number of layers of graphene. And whereas a single layer of graphene is 97% transparent, if you have many layers, it's black, right? Because each layer absorbs 3% of light. So when you're writing, you're rubbing off on the paper, say 20 layers of graphene or 30 layers of graphene, and that's why it looks black. And so that's getting graphene from pencil. And what's interesting about graphene, why it's so remarkable, is all these world-leading properties are in a single material, right? So mostly, copper's a great conductor, but not so good for a number of other things. All these properties in graphene, and it's unique in the world because of this, and that's why it was called the wonder material. And so what companies did, they said, well, this is wonderful because we can build computers which are, 1,000 times faster from graphene. And so the problem is scaling up. And so companies like Intel have spent $750 million trying to scale up flakes of graphene to larger areas that they can actually manufacture from. And IBM has spent, IBM has spent $3 billion and Samsung over $2 billion. So, and these companies have been doing this since the discovery of graphene, and they've largely stopped their research because they couldn't solve this problem of scaling up. And this gives some, so where are the predicted wonder electronic products? And they're not there. So, and this gives some headlines. So on the left-hand side, this is from the World Economic Forum newsletter. And that heading is graphene, soon make your computer 1,000 times faster. That was probably in 2015, it hasn't happened. Bosch finds graphene magnetic sensor 100 times more sensitive than silicon. They assembled it by hand from tiny flakes, it wasn't manufactured. And then graphene filters changed the economics of clean water. So these things all predicted, and they haven't happened. And Bosch actually issued a press release in 2015, and they said, we've created this sensor 100 times better than silicon, but unlikely to compete for 5 to 10 years because of the current lack of large-scale wafer-based and transfer-free synthesis techniques. There is a larger scale technique available called CVD, chemical vapor deposition, but you deposit the growth gases on copper, and the copper acts as a catalyst to decompose these growth gases, and then you've got graphene on the copper, and you can't make a device from that, so somehow you had to get the graphene off the copper and put it onto something more useful. I gave this as a sort of challenge to my group and said, you know, we need a new way of making graphene. And we were using equipment called MOCVD to make a gallium nitride, metal organic chemical vapor deposition. And one of them came to me one day and said, why don't we try this? And I said, well, it's probably not going to work, but, you know, why don't you try it? And it did work. So this was a postdoc, Simon Thomas, and they used metal organic chemical vapor deposition, and we found you could grow graphene using this technique. No one else in the world had done this. And today, although this was patented in 2015, we are, as far as I'm aware, the only people in the world using this technique today. So others have tried and failed. Now, as far as I'm aware, maybe something's happening in China or another country, and it's secret and we don't know about it. But as far as I'm aware, and we have the patent on this. So there's no metallic contamination from a catalyst because we don't use it. We deposit directly on the substrate we want to deposit on. And it's really promising for next generation materials. And so we set up a paragraph company to exploit this research. And you have to raise funding. And so we got funding from venture capitalists. And we set up in 2018. We've already got 75 employees, right? So again, you're giving people jobs and doing really interesting science. Now, you should think about, right, if you have ideas, think about setting up a company. It is not difficult. You register the company at the company's house. I think it costs £100, right? So not so expensive. And then we look for premises on the Cambridge Science Park, and they're really expensive. And so we looked all over the country, and then someone told us that, it's on some sort of timer, someone told us that a farmer in a village called Somersham has put these big sheds on his land, and he said, it's an industrial park, come into my industrial park. And these were sheds which were empty, no electricity, no water, just sheds with a couple of doors in and very few windows. And so we got one of these sheds, and we had to bring in the electricity from a power substation nearby. We brought that in, we brought in the water. We moved in February 2018. It snowed the day we moved in, and we knew that because we found there was a hole in the roof, so the snow came in. So we got to the farmer and said, mend the hole in the roof, which he did. And then inside this building, so the windows you see are windows that we put in. So there's a couple of doors which were there already. And inside the building, you can put up really nice buildings. You know, you put up we've got carpeted offices and a clean room and so on. And so it's not difficult to set up a company if you've got a really good idea. So you may have now, but towards the end of your undergraduate degree, or if you do research, when you're a research student, you may have a good idea and think about setting up a company. So I'm watching the time because I should finish quite soon. I think that's okay. This is right. So this what we've made. The first product is a Hall sensor, and some of you may know what the Hall effect is. Otherwise, you'll find out in your lectures. But basically, you can measure magnetic fields using this, and our sensitivity compared with silicon Hall sensors, which are the standard ones, the silicon Hall sensor has a sensitivity of 70 volts per amp Tesla is a rather curious unit used. Compound semiconductors, these are quantum well Hall sensors, 850. The original Bosch one, if you look at their paper, it was 1250 and they couldn't manufacture it. Ours is 2000. It's manufacturable, so it's 30 times better than silicon, and also it operates at really low temperatures, right up to room temperature. The minimum of silicon is 230 K, so you can't do cryogenic work with the silicon. Maximum operating temperature is 450, and we're trying to improve that. Highly radiation resistant. operates in really high magnetic fields, 30 Tesla. I mean, Harry talked about fusion reactors. It turns, fusion reactors have very high magnetic fields, and they can't measure them easily. So we've got some sensors with a tokamak, and they're trialing them in their fusion. So this will help, the next generation of energy hopefully from fusion reactors. 100 times lower power consumption of silicon. So again, save lots of energy. 100 times less is very large, and operates in harsh environments. And not only can we measure magnetic fields, we can measure currents, because if you've got a wire carrying a current, you'll all know there's a magnetic field around it. You can measure magnetic field, and so measure what the current is. This shows you can measure the speed of rotating shafts. So this shows you a couple of a couple of pieces of metal rotating, and then this flashing thing, that's a magnet with a whole sensor in front of it, and the metal changes the magnetic field as it goes around, and so you detect these changes of the whole sensor, and so you can measure that speed, or you can measure the speed of this gear wheel going around. And so in motors, it's very, very useful to be able to do that. We're talking to CERN about this. The next upgrade of CERN, they're going to have superconducting magnets operated at liquid helium temperatures all the way around. It's in Geneva, CERN, and 27 kilometers long ring, and they want 10,000. They want to know what the magnetic field is all around this device extremely accurately. They want 10,000 sensors. Ours are the best, and they've got a partnership with us at the moment. Batteries, early stage detection of first signs of failure. You don't have to drive an electric car and the battery has a failure. So we want to mount our whole sensors along here and detect tiny change in magnetic field. If you've got a defect in the battery, then the current will locally vary, and the magnetic field will vary. You detect that, and you say there's something wrong with this battery or this battery cell. And this is almost the end. So this is really recent. This is a research student I've got starting this week. He's just started from India, and this is his project. And what I'm going to say to you, there's lots of projects like this in Queen Mary. If you want to be research students, just think about it. Anyway, bowel cancer, 700,000 deaths worldwide from bowel cancer. Second most common cause of cancer in women, third in men, right? So those people all listening, statistically, some of you are sadly going to get bowel cancer. What we want to do, this is the idea. Hi, Colin. What we want to do, this is the idea. I'm just finished. It is to have some magnetic nanoparticles, coat them with a protein which attaches selectively to precancerous polyps. So such proteins exist, so this can be done. And then we squirt this up the bowel, and if someone's got a precancerous polyp, that's a polyp with just 1 or 2 cancer cells, then this magnetic nanoparticle will attach to them. Then we put our ultra-sensitive magnetic sensor in a robotic arm inside the person, to insert up the bowel, and at the moment our sensors are centimetre by centimetre, so we want them a bit smaller, right? If someone's pushing something up your bottom, right, you want it as small as possible, right? So not a centimetre. So we're working on it, and that's students going to work on this, and that's doable. Detect the particle, detect magnetic field, know the particles are there, hence there's a polyp there, and the surgeon can just snip it off with his robotic arm. This could save literally thousands of lives each year, health service money. A new research student started this week. Final slide. So gallium nitride is revolutionizing lighting, saving lots of energy. New way to make graphene, work very well. And then you could be a future PhD student in materials at Queen Mary, and you could help to change the world. Thank you very much. Any questions?